Hello, good morning, everybody. It is my great pleasure to introduce Søren Eilers from Copenhagen. He has been my colleague and collaborator for quite a long time. In particular, we have together an European grant operator algebras that one can see, and we also have Simon semester in the Banach Center. So next year we should have a meeting here in Bend-Level, Søren and I, devoted to graph algebras. From what I could gather, Søren, from your CV, you are a very Copenhagen person. You've been educated in Copenhagen. You are a professor in Copenhagen, so really it sticks out. You are the Copenhagen man. And so Søren is now a professor, of course. He's a well-established operator algebraist and a genuine guru of graph sister algebras. So if you want to do graph sister algebras, he is among the best people in the world to talk to. Of course, he is an author of numerous papers, recipient of many grants, supervisor of many PhD students, and editor of some journals, for instance, Mathematica Scandinavica. And Jacek Miękisz, one of our co-organizers, should like it. Søren was also for a time the president of the Danish Mathematical Society. So Jacek is currently the president of the Polish Mathematical Society. So you can speak like presidents to each other. Okay, guys, without any further ado, it's my great pleasure to welcome Søren Eilers. Søren, the floor is yours. Take it away.
Thank you. So thank you for the introduction and for the invitation to speak here. So I'm going to talk about some aspect of mathematics of Lego. This is somehow as Piotr is pointing out, I've spent most of my time in Copenhagen and hence in Denmark. So Lego is a Danish invention, but actually in another part of the country. So I'm going to tell you just briefly how I got involved in this. That's more of a computer science problem than it is a mathematical problem, but then I will sort of slowly move on to the math side and try to convince you that there are some very interesting mathematical problems, which unfortunately I cannot solve. So I'm going to have to resort to a little bit of specialization at the end. This is what mathematicians often do. If a problem is too hard, you can make it easier by changing the rules. And so I actually have some real math at the very end, but the basic problem remains open. And I think in a sense, this is interesting as well. Okay, so the starting point for this whole thing for me was this poster. It's written in Danish, so I don't expect that you understand, but it's a picture that I saw in Legoland in Billund, which is in Western Denmark. So this is an amusement park. I went there in 2002 with my daughter, who is now 25, and so I guess she was 5 at the time. And it was a very rainy day in the middle of the summer, and we had to go inside because it was just pouring down. And then there's a little place where the kids can play with Lego, and I was sort of walking around and I found this little picture. So what it says is, it's supposed to be at a patent office. You can see the date. It's January 58. And this is when Lego got the patent for the Lego brick. So I have here a supersized Lego brick here. So the point of a Lego brick and actually the point of the patent is these things here. So that's the underside, which sort of makes them click together in an appropriate way. So actually Lego had bought the shape from a British inventor, but it didn't work very well. So the patent is for this part, which makes them sort of click together and stay together. So we see sort of a nondescript patent office clerk, I guess, and he's asking, please state how many ways you can combine 6 bricks. And then there's a picture of Kjeld Christiansen, who was the owner and the inventor of Lego for many years. He's the father of the present owner. And he says, we are still doing the computation. When I left this morning, we had reached 102,981,000. So my take home from this, and I have to say I wasn't there very long because my daughter was not willing to be inside for a very long time. But actually, the first thing I noticed was the 3 zeros at the end. I thought this was weird that somehow this number, whatever it was, would be a multiple of 1,000. So I now know that there's supposed to be, it's sort of a round off error. But this is what I started thinking about. And I started thinking about how do you compute this number? And I was under the impression that this was old. I also now know that this drawing was made in the 70s, late 70s probably. But somehow I was, the patent is old. So I thought this is something that was done pre-computer. So it didn't seem likely to me that Lego would have a computer when they did this computation. And it seemed strange because I thought this would be a hard problem somehow. It seemed strange to me that they could solve it back then. So this is sort of what I was thinking about. But then I had to leave and I stopped thinking about it. Okay, so then what happened was I forgot about it for a couple of years, but then I have a friend who is in the advertisement business, and he works for another Danish company that produces, not as well known as Lego, but fairly well known. It's called Montana. They make office furniture, and it's something, they have this sort of square. It's like a bookcase, and you can put shelves in different ways, vertically and horizontally, and they have many colors, blah blah blah. And they asked me to compute how many ways you can do this. So they paid me a small amount to do this, but it was actually very easy. I plugged it into Maple, which is sort of a computational program, and very easily I computed the number, which was a 280-digit number, so very, very big because there's many colors and so on. So I told this to them, and they were happy and put it in some advertisement. But then I was thinking, this is a bit like Lego, right? This is a bit like this old number that I had seen, and not being at Legoland at the time, I Googled it, and I found this thing from the company profile in 2004. So actually, you can see the number has now increased. It used to be 3 zeros at the end, but now it's 5000, so 500 more than was on the poster. And on the poster, they say that it's at least this number, and now they say it's exactly this number. So this is when I started working on it fairly seriously, and it took me some time, a couple of months, I think, in order to actually figure out that the number that was given there is not correct. So let me be a little bit formal. So these things are, I mean, you have to be careful when you make these definitions. So BN is the number of buildings that you can make with n 2x4 Lego bricks. And there are some rules, right? It has to be what I'm calling contiguous. So that this just means that the whole building is sort of put together. This means that if you sort of lift one brick, everything comes up with it using this clutch power that we just discussed. Also, the bricks have to have sides parallel to each other. So, I mean, you could turn something like this, but that's not allowed. So everything has to be either the two long sides are parallel or the two long sides are perpendicular. And then we identify buildings if they're the same up to rotation. So, for instance, this building here is the same as this building here, of course, but this building here is not the same as this building here, right? Because we can sort of distinguish the top and the bottom of a Lego. And of course, they're also the same if we sort of rotate them around. I mean, this building here is the same as this building here. So that's the number I'm calling BN. And the number we're talking about is B6 when we have 6 bricks. And I'm also going to talk about a special class, the towers. Those are the ones that have the maximal height. So what happens here is that we can start, if we sort of start small, this is always a good idea when you're doing a math project. If 6 is too hard, go back to the easy cases. So if there's only one, of course, there's only one way of doing it. And if you have 2 bricks, the answer is, I would say, 24. So what you can fairly easily compute is that if you take the bottom brick, so I'm thinking of the green one as my bottom brick, and you fix that, you keep it still, then you want to affix the top brick, the red one. And how many ways can you do this? The answer is 46. Because if you sort of go, if you say now the long sides should be parallel, then you can go 1, 2, 3, 4, 5, 7 in this direction, and 1, 2, 3 in this direction. So that's 7 times 3, that's 21. If they are perpendicular to each other, you can go 1, 2, 3, 4, 5 in each direction. So that's 5 times 5, it's 25. So the sum is 46. So I've shown you a picture of all these 46 ways. This is sort of a joke. So I visualized it in the way that you usually visualize the 46 human genomes. And there's something special about two the genomes, the X and the Y. And this is exactly the same in Lego. So of these 46, 2 are special because this particular configuration has the property of being symmetric. If I turn it around, I get back to what I already had. And if I take this one and turn it around, I get back to what I already have. So of these 46 choices, we have 2 that are symmetric and then 44 that are not symmetric, which means that if you take one of them and you turn them, then you get something that you already had. So when I say the number is 24, it's the computation where I'm saying, okay, I have the 2 symmetric ones, those are 2. And then the remaining 44 ones, they come in pairs, so I have to divide by 2. So there's 22 of these because we identify this one here with this one here. So you can see I have that twice. So that's why the number is 24 and not 46. And then you can very easily generalize this if you only count the towers. So the towers are those that have maximal height. So you have sort of a choice process, which is exactly the one that I showed you for 2 bricks. If I fix one brick, then I have sort of 46 choices for the next one. Then I have 46 choices for the next one, and so on. If I have 6 bricks in total, and then that gives me 5 times I have to choose between these 46 options. But now I have to be careful with symmetry, right? So I have to count the symmetric buildings, and there are exactly 2 to the 5 of these because I have 2 symmetric ways of making a building. So that's 2 times 2 times 2 times 2 times 2, it's 32. So we take sort of 46 to the 5th, subtract 32, divide that by 2, those are the non-symmetric buildings, and then we add back on the 32 ones. And then the number that you get is 102,981,504. And of course, this is the number that they were trying to give us in the on the poster and on the company profile from 2004. And this you can very easily generalize, but of course, we're not done, right? We have only counted the towers, right? We've only counted the towers, and that is easy as a mathematical problem because it's something you can subdivide into sort of 5 choices, right? But when you look at a general Lego brick building with 6 bricks, so this is one of the ones that I'm counting when I'm looking at B6, then you can see that the choice process is much more complicated. There's no sort of direct or obvious order that I'm doing things. And whenever I make a choice, it influences the following choices, because when I put my brick number 2, has a big influence on where I can put my brick number 3. And on top of this, we have to sort of adjust for the non-uniqueness of the way that we count these things. So this is the problem I thought they were solving, and I couldn't see how they could do it without a computer, and I still cannot see how to do it without a computer. But then when I realized, of course, that it was wrong, it was fairly easy to write a computer program and do the computation. So this is the history of these numbers. So actually, the number 102,981,500 was computed by another Kirk Christiansen, a guy called Søren Kirk Christiansen, who is the cousin of the present owner. So the guy I showed you a picture of is his uncle. He's a chemical engineer, and he worked at Lego for sort of color proofing the bricks, and they asked him to do this computation. And being a chemist, he was actually very good at thinking in terms of symmetries. So he made this completely correct computation, and he told people, it was in the newsletter of the Lego Corporation, he told them, I'm only counting the towers. But then you can sort of see, then the PR people, like my friend, they got involved, and they stopped saying this is at least this number. They're saying this is the number, right? So this is the kind of thing that can happen. And actually, I was the first person, I'm pretty sure, who did the computation for 6. It's 950,103,765. That took me about a week because I had written a very bad program. So it was a very inefficient computation. But I actually found out later that somebody had figured out that it was wrong with 3 bricks, because if you only count the towers as 1060, but there was somebody on a Lego sort of Lego enthusiast discussion group who computed the correct number with 3, which is 1560. I know who he is, but he wants to be anonymous for some reason. Okay, so this is sort of what I could do in 2004. I wrote to Lego and I asked them, yes, I told them it's wrong, and they actually fixed it very quickly. I was a little bit surprised that they somehow believed me right out of the box. And what has happened now is that there's something called Lego House in Billund, which is a place where you can. It's more like it's not directly involved with the Legoland theme park. It's more like a science park type of building. And when you leave that, you get your own combination. So they give you 5, 6 little bricks, and then they say, okay, this one is yours to keep. And this is so I show you the picture of the one that I have. There's also a picture of a math professor there, and I'm a little bit afraid this might be me, but I don't usually do chemistry this way that this guy does. So anyway, so this is sort of the I'm just telling you this as this is mainly a fun story of how to use math to talk to people who don't necessarily like math, and this was definitely my starting point. But actually, there's already, we're beginning to see some interesting problems. The first interesting problem here, I would claim, is more of a computer science problem than it is a math problem, and that is compute these numbers as far as you can. Right? And the programs that I have written, so actually there was a high school student who did a project with me around the same time. I asked him to recompute the numbers, and he got the same numbers as me, so that's also why I feel fairly confident. We wrote a program that could take us to 8, so we could compute the number with 8. That took me something like 500 hours on a mainframe computer, the kind of thing that we used to have that back then. And then I gave up because it just like the numbers grow with sort of 2 digits every time, the computing time also sort of grows by a factor 100. So, I gave up. But actually, it's been done a lot further than I thought I would ever seen. So there's a guy called Johan Nilsson who did the number with 9. He did it this way, that he was in charge of the computers in a math department in University of Bielefeld, and he sort of went in and did it so that when his colleagues left, it would do Lego computations. So it's sort of at night he would do this computation. So he could do it in only 2 months, but he was cheating using something like 200 computers. So that's what the computer scientists would call a parallelized solution. So the guy who holds the present record, Matthias Simon is his name. So he did the computer on 1.5 computation on 1.5 computers. So a half because he was borrowing his daughter's, but he actually destroyed her board, and so he had to replace it. And then after that, she would not let him use it. So he did it on essentially on 1 computer, but it took him 22 months. So that's a very long computation. He did something very, very clever to do this, but don't really have time to explain. So let's move on. But this is something. I mean, this is what we know, right? And maybe somebody who worked really hard and was clever could do 11. But I would be very, very surprised if somebody could tell me 20, for instance. And that's of course because I don't have a nice formula like the one that I have for the tower. So we get into a territory which is computationally demanding. Okay, now, so let's move on now to something which is a little bit more mathematical, and this is what I would call the asymptotics of this situation. So this is a very common way of dealing with questions of this type. So instead of sort of looking at the individual numbers, I want to say something about how the sequence of numbers, which is now well defined, how will this grow? So there's several ways you can make sense of this. What you, for instance, can do is that you can take the nth root of bn and see if that converges. So if that converges, that's a bit like saying that bn is roughly c to the n, right? So this means that bn is an exponential growth with a base number, which is c. And the base number, of course, is really what you would like to know, right? Because that sort of governs the most fundamental behavior of the growth of this sequence. So, and you can sort of do the same with successive quotients. You can do bn plus 1 divided by bn. Again, if bn is roughly c to the n, then bn plus 1 is roughly c to the n plus 1. And then when you divide by bn, which is c to the n, then you just get the c out, right? So in both cases, you will expect that this will converge to the rate of growth of the of this number of buildings, and this is often called the entropy. Maybe after you take the logarithm, this is also often called the entropy of this situation. But you can also try to do something which is more precise, and this is somehow you could say, well, it's reasonable to assume that the rate of growth of these buildings has the form some constant times a power term n to the something times an exponential term gamma to the n. Right. So this is these questions are sort of the lower question. If the answer is yes to the lower question, then the answer to the two upper ones is yes, it converges, and the limit would be gamma. So if you're familiar with power series and how to compute radius of convergence, so this is like using the what's it called? Is it called a root law? Or this is basic math. I only use it in Danish, and the other one is a fractional law. Right? So this is how you can compute the radius of convergence of a power series, and actually that's exactly the same as the rate of the growth of the coefficients. So this is a question I would like to ask, and the problem is that it is hard to compute, and it's actually not even clear that these numbers are defined. So I worked on this shortly after I did these computations. I worked on this with a colleague of mine who's a mathematical physicist, and it turns out that if you want to find some literature on questions of this type, you really should look in the literature of mathematical physics, because they count objects, for instance, in models of gas and so on, to describe the behavior of that, and they look for sort of critical temperatures, which is very closely related to these types of entropies that I've talked about. So I realized from the beginning that I would need to know some more math physics, which is not really so much part of my day job background, in order to understand this. So and what my colleague taught me is that what we could also try to do is, instead of counting all these buildings up to rotation, we can also say that we count something different, which is almost the same. You take a base brick and you fix it. So just like before, you take a base brick and you fix it, and then you sort of say, this is the only brick which is in the lower layer. And then on top of this, you can build whatever you want. And that has the advantage that we don't have to think about symmetry, because we can just fix it so that we hold this still, right? So now the number 46 would come back, because it's the number of ways of doing this with one fixed brick in the lower level, and then one in the second layer. And then the point of doing this, so I've shown you these numbers as far as I know them, that it's very easy to see that these F numbers are what is called super multiplicative. So this means that if I take the number of F buildings with N bricks and I multiply it with the number of F buildings with M bricks, this is, did I say super? I mean sub, sub multiplicative. This is less than F of M n plus M. So the point is that I always have that the product Fn Fm is less than Fn plus M. And this is actually true also of the B numbers as far as I have computed it, but it's very difficult to prove this. So that's why I'm looking at the F numbers instead of the B numbers. And when we're talking about the rate of growth, it doesn't matter, because Bn, Fn plus 1, for instance, is sandwiched between Bn and B4 times Bn plus 1. That's because whenever I have Fn plus 1, I could just remove the lower one. I get one that has is counted by Bn. And if I sort of go up to bn+1, then I have more options, except that I have to keep track of the symmetry question, and I have to multiply it by 4, because actually there are buildings that have a 4-fold symmetry, right? You need at least 8 bricks to do this, but it's fairly easy if you sort of do like a chimney type of building in Lego, which I'm sure many of you have tried. You can find one that is symmetric already after you turn it 90 degrees. So actually some buildings you would have to divide by 4 and not just by 2 in order to sort of adjust. But then when you have this, you can actually prove that that there is a limit of these numbers. And that's because if you take the logarithm of the equation down here, you get that the logarithm of fn plus the logarithm of fm, because of the multiplicative rule that defines logarithm, is less than the logarithm of fn plus m. And this will make the sequence sub-additive, and then there's a lemma often called Fukada's lemma that shows you that this sequence will converge. So this means that we know that it converges, and so what the observation we did is that if you do this nth root thing, this will converge, but it only converges on the extended real axis. So it might converge to plus infinity. Right? And for a long time, I actually thought this would be the case, because if you sort of look at these numbers, they grow faster and faster. So that would sort of mean that it grows faster than an exponential growth. But my colleague with his background in mathematics and physics, he was absolutely convinced that it would be that the limit would be a number, not just infinity. And we came up with this way of proving a bound. So what we did is, right, this is sort of the opposite of what Lego was doing, right? They're trying to show big numbers in order to say that this is a very useful and flexible toy. So what we're doing is the opposite. We want to put an upper bound to how flexible it is, right? So this is not something you would use in your advertisement. So the way that we did it was that we somehow came up with a way of making a recipe for building Lego buildings. And the way it was done is, so you should look at the right. You have these are hexadecimal numbers. So I mean numbers between 0 and F, which means 15. But they're sort of codes for making a building. So I'm trying to make the building that's on my card from Lego. So the way it works is that you have 5 choices. So you have the base brick like before. And then what it says is that insert 0 into 5 from above perpendicularly. This is, so I made some sort of enumeration of these studs. Doesn't matter. I think this is 0, 1, 2, 3, 4, 5, 7, 4, 5, 6, 7. And then I take, so number 0 is this one here. I put it something like this. And this is the sort of beginning of my building over here. And then I keep on going. But what's important here is that I never say you should insert brick number n into brick number m, because that would be a problem. That would grow too fast, because as I get more and more bricks, I would have bigger and bigger numbers to give names to my bricks that I'm affixing. And so if I had a code like this, this would actually become longer and longer the more bricks I add. You should sort of think of billions of bricks, right? I'm going to infinity, so that's part of the thing that I need to worry about. So the point here is that I'm never saying this is one particular brick. It's more like I have one brick and this is sort of it. That's the one I'm building on. And then I take the 2, so that's the lower one that you see down here, right? Then I'm putting 2 things on top of that. And then I'm saying, okay, now I'm done building on this and I move to the next one. So then that becomes this one. This one here I'm not building on, so I move to the next one. That's this one. And now I put something on that, and so on. So the point here is that there's a long line of bricks, and I'm just taking one and putting it on. And when I put it on, that's when it gets a number. And that's when it sort of goes in the line that will eventually be it for putting something on. So this works. And you can actually, if you want to be a little bit more careful, you can make upper bounds that are not as high, right? So I'm using hexadecimal numbers. It's sort of showing my age. It's when I was a kid and I wrote computer programs on old-fashioned computers. You would have to do some programming in machine code and hex codes and so on. So this is the kind of thing that you would do there. And actually also then you would be very careful with space, because the computers we had did not have a lot of space. So you would be very sort of conservative with space. And what you can do here is that you can take this specification that I just showed you, where I'm using five hexadecimal digits in order to specify what I'm doing to one brick. I can sort of pull this down to 2.5 if I'm more careful. And this will then prove that an upper bound for the rate of growth for Lego is 1024. So this, what I've shown you this far is that the rate of growth is at least 46, because that's when you get by just counting the towers, and it's at most 1024. So now I know it's not infinity, it's a number in that interval, right? But also, of course, I've given you a really terrible estimate of this number, right? It's like saying that, you know, my best friend is somewhere between 10 centimeters and 5 meters high or something, I mean, which is true, but not very useful. So we worked quite a lot on this.
Sorry, could you please, could you go back to the previous slide?
This one here?
So when I look at these two, no, this one with two propositions. Yeah, so these two propositions look identical, except that they have different outcome. So could you please clarify again what's the difference in the meaning of these numbers BN, FN, because you get different results. So there must be some different standing assumptions.
Yes, so I'm always working on the FNs because that's somehow easier.
Okay.
In the first case, what I'm claiming is that if I take one of these buildings that I count by FN, I can describe this using 5 times n hexadecimal digits. And this is the specification that I have here. So you can see I need to use an F to move it forward, and I need four bits, these are neither bits nor bytes, these are digits, hexadecimal digits. So if I have 2, it's a byte, to specify where I'm putting the things. So that's it costs me 5 hexadecimal digits the way that I did it here. So the claim is that if I take all this information, I can compress it into less space. So what I can do is instead of using 5, I can get by with 2.5. And the ways is, so I only have 8 of these, right? So to specify which one I'm putting, I just need 3 bits for that. And then to specify if it goes above or below, I only need 1 bit for that. And to specify, and to specify, and then I have to be careful with this F because it shouldn't be confused with other things. But the point is that I can sort of compress this and I can get down to 1024. So the only difference is that here I have 5n and here I have 5n over 2. So it's just sort of a compression of information. Of course, and what I really want to know is to, I want to bound this. I mean, I have given up, to be frankly, I've given up computing this number exactly, but I would like to sort of bound it. And the best bound we have, which is now actually pretty old, something like 15 years. It's somewhere between 78 and 177. So we worked really hard until the gap was less than 100. So, and then we gave up. But it's, I mean, and the way we do this is that from below, we just find many buildings. And that's sort of a generalization of counting only the towers. From above, we could only get so far with these kinds of restrictions that we came up with. I think we could get to something like 250, but then we found a paper by Klarner and Rivest. So this, I'm coming back to this, but this is in the context of what's called animals or polyominoes. So counting those, there's a method there that we could steal. Rivest is the R of RSA. Compensation, a very famous mathematician and computer scientist, and Klarner is the guy who sort of started the study of these polyominoes that I'll come back to. So we could sort of use a combination of math and computers. We can get it down to this, but of course it's not a very good estimate. My guess, based on some Monte Carlo experiments where you sort of use probability, randomness to estimate these numbers is that it's around 117. That's what I'm expecting the real number is. So I mean, so this sort of tells you, I mean, even though we are sort of using modern computers and clever methods, we're not getting very close. So this is when I'm beginning to make life a little bit easier for myself. I'm going to move down in size and work with 2x1 Lego bricks. So of course, the smallest Lego, sorry?
Sorry, I have a question at this moment.
Yes.
So still we don't know whether in this expression for Bn is some polynomial factor, yes? The main part grows like an exponential, but still it is possible that there's some polynomial times the exponential, yes?
Absolutely, and so that's a good point. I'm going to discuss it in the context of 2x1s, but let me say what I think I know here. So the question is, I still believe the answer is yes to this question here, and my guess is that the number that I'm calling gamma, which determines the exponential growth, is roughly 117. So there's a constant alpha, which I don't remember, it's not so interesting, but the beta is the power of the power term or polynomial term. Mm-hmm. And I'm pretty sure this is minus 1.5, so minus 3 halves. And this is actually a very common, this fits the observation. This is a very common constant which comes up when you count sort of three-dimensional problems in mathematical physics. So I mean, I'm saying I'm sure. I mean, that's sure in the way that this looks right. Of course, I have no proof, right? But it's very clear from the data that it's not a pure exponential growth.
Exponential.
Right, which actually, you know, I showed you this formula here for the towers. This, I mean, so I had to do this little adjustment for the symmetry ones, right? But this is more or less exactly exponential, right? It's like, roughly speaking, it's 23 times 46 to the n. So it's more complicated, which you would expect, of course, in a situation like this. But I'm going to show you. As soon as I make life a little bit easier for myself, I'm going to show you some results, and actually some of them have proofs. But this is sort of all I can say about the 2x4 case. And of course, the 2x4 case is the most important one if you're a Lego enthusiast. But if you're a mathematician, you know, you want to look at the most basic, interesting case, right? So the most basic case is a 1x1 brick. You can make exactly one building with this, so that's not interesting. So I'm going to 1x2. So this is.
Okay, thank you.
Thank you. And that's a very relevant question, of course, but we'll get to that. Okay, so I'm going to do something slightly crazy now. I'm going to generalize the Lego counting problem to arbitrary dimension. And this is something I thought about quite a lot. So of course, the Lego brick is a 3D thing. So you can ask, you know, what would it be in 2 or 1 dimensions? And of course, that perhaps is not such a hard problem. This is like, you know, the 2D Lego is like you just play with Lego as you usually do, but you make the rule that you can only sort of work in one plane. And then I guess if you want to make it one-dimensional, you'd make the rule that everything would sort of have to go directly on top of each other, and then it's nothing happens. But what if you had 4 dimensions or 200 dimensions? What is the right way of thinking about a higher dimensional Lego? And so as I said, this is something that confused me for a while, and I think I have the right way of doing it now. So what I'm going to say is that there's something special about one of the dimensions for a 4-dimensional Lego brick, for instance. And that's just like for a 3-dimensional Lego brick, there's something special about this dimension, the one that we usually think of the top and the bottom. This is where we attach the buildings to each other. So if we just take any D, this is now my dimension, and I'm saying, okay, what is a 2x1 brick? It's a cuboid. So this means that this is a product of some intervals. And these intervals have length 1 or 2. And exactly one of them has length 2, and the rest of them has length 1. And we're also making the rule that there's something special about the last dimension that's not allowed to be 2. Just like these buildings, they're 2x4, and they're always 1 high. This is not entirely true. Lego has some products that are 2 or higher, but most of them are only 1 high. So what I'm saying is that what the buildings that I'm thinking about, they are made this way. So it's a connection it's a collection of bricks, generalized bricks, and they have the dimension, all of them 1, in particular the last one, except for 1. But I also have to tell you
so
how
you can think about it as some kind of time component, right? This is like
if you want
time
to,
component
exactly,
in
if you want to,
space-time.
you can sort of imagine a 4-dimensional. I mean, the way you could think about this is, suppose you wanted to explain to a 2-dimensional creature what this is, then you could sort of say, well, at this time, so at this time it doesn't exist. Then at this time, this is when it starts, and then at this time there's a little knob which sort of grows up and comes down. You could do the same with 4. I've actually tried to visualize. I have a friend who does this kind of things, and I asked him to see if he could do like a patent for a 4D Lego for me, but he's sort of given up. So, but I haven't told you how you build these together, right? So I need to show you this. So so this was just a definition of a brick, and then what is a building? Well, the first rule is for the buildings is that just like when we build with ordinary Lego, we will sort of fix the corners in integer positions, right? So I'm not sort of moving them back and forth. They will be fixed at integer positions. So this means just that all the entries are integers. Then if I have two different indices and I take the interior of these buildings, so I'm just taking the open interval and cross them with each other, then I should get 0. Right? This is just like, I'm sort of thinking of the ends of 2 Lego buildings as they can touch, right? But the interior cannot touch, they cannot overlap. But then how do you check if a building is connected? Well, I just want to use the ordinary mathematical definition of being connected, which means that any point in the configuration and another point, you can sort of move. I want to use path connected. You can take a path that goes from one to the other. But the point is that to do this, I have to throw away the boundary on the sides of the Lego and keep only the boundary on the top and the bottom, because this is where I glue, right? So I want to take, so I will sort of take the half open brick, right? So it's open except in the last dimension. And then you can sort of check, this is precisely the same definition as I gave you for 3 dimensions. So what I'm trying to say, so I mean, maybe this is a little bit complicated, but the idea is that what's special about a Lego brick is that it's a fixing only in the D dimension, right? So only in the, I mean, you cannot sort of, this is not a Lego configuration, right? Because they don't sit together. This is a Lego configuration. I have to sort of use the set dimension to get to that. Okay, so this is of course we can always discuss this, right? And since we don't have 4D Legos, I mean, who's to say what's right? But this is my definition, and now you can sort of do the very same. I will just say I define the B and D, that's the n-dimensional buildings, and I identify them up to what more mathematically you would say the isometries of the first D-1 dimension. So this is sort of a rigid transformation. I had only rotations. I'm saying isometries that would allow a reflection. I don't want that. So what are those called? This is just the special orthogonal group, SO. Right.
Yeah,
this is what I have in mind. Only rotations. Oh, so that's actually wrong. And then I could do the same with F. And just like before, we can make sure that this number exists. And now I would like to know it, right? So what is the number and how does it vary with D? I think that's an interesting question. You can sort of make some very crude bounds. And the things that I would like to know is, for instance, does it grow with the dimension in a linear way? This, I think, is to be expected if you look at similar physics problems. So what I mean by this CD plus O 1 over D, this means that if you take the correct number and you subtract C times D for some constant D, you get something which goes to 0 roughly as fast as 1 over D. And then, of course, you can ask the same. I mean, is it true if you take these fractions, will it converge? And can you find alpha, beta, gamma just like before, which approximates? I should say this explicitly, by the way. I do not know, even for the 3-dimensional Lego, if this quotient converges. It's an open question. So so what you can do is that you can sort of say, okay, now I can have a computer do my computation for me, and then you can say, how do I estimate these numbers? And really what I'm interested in is estimating the gamma and the beta, right? So the gamma is the rate of growth, and the beta is the power that you see in this power term. And this is hard because, I mean, these are numbers that I don't know very well, but there's a trick that is often used in the physics literature. So you take these fractions, and then you sort of say, well, if you believe my formula, then the numerator looks like this. I just put in n plus 1 instead of n, and the denominator looks like this. And then when you factor out, you get gamma out as a constant, and then you get 1 plus 1 over n to a power beta. And so let me show you how this looks in Maple. So I have this little experiment here. So these are the, I mean, I had a program do these numbers for me for some time. Of course, as the dimension grows, I have more and more options, and it takes longer time. So so this is somehow the reason why this is sort of a triangle is that if I get down in this corner, I have many bricks and many dimensions, and it just takes too long. So I don't really have that. But then I can sort of, you know, ask, I can just think of this as something that came out of a mathematical experiment. So it's like, you know, if I had done something in a lab, and then let me show you what this looks like as a graph. So it takes a little while for Maple to do this. So this is what I'm doing here is that I'm taking my observation. So you see at the very bottom, I have 2 dimensions, then I have 3, then I have 4, and so on. You can see I get fewer and fewer observations. And what I'm plotting here is on the x coordinate, I'm plotting 1 over n. So my observations here start with a half, because that's 1 over 2. Then I have a third, that's 1 over 3. Then I have a quarter, and so on. Because these are exactly the numbers that I expect go into a nice formula. And then you can use a sort of least square approximation, and you get these things. So the dotted ones, I threw away 2 first terms, and in the other ones, I threw away just 1. And I get these sort of fairly nice fits. And then you can sort of go to infinity, which means going to 1. And this is my estimate of how these rates of growth behave. So you can sort of see, I mean, some of this is based on very little data, so you shouldn't really trust it, right? But you can sort of see there seems to be a nice systematic growth in the gamma numbers, which is what I was somehow predicting. And then if you look at these fits that I made, so I get something like 1,0,1 in 2 dimensions. I get 1,67 in 3 dimensions. So this is what I'm claiming it should be 1.5. And then these numbers actually tend to decrease. And this is a little bit weird. I don't think this is right. And this is probably because I don't have enough estimates, right? But you can sort of see I can, if I had the numbers I have, I computed over about a week. So this, of course, I could get more if I was working more with computers, but this is sort of what you can see, and there's at least some patterns here that I think might be interesting. But I have to admit that I don't really know what's happening. In mathematical physics, there's a lot of interest on the rate of growth of the power term. So it's well established that if you have 2 dimensions, you should expect to see 1 over 1. I mean, sorry, you should see the power should be -1, and then in 3 dimensions the power should be -3.5. And then the question is, how should it grow? Should it be next time 2, then 2.5, and so on? And it seems to be that's not the case. There's more interesting behavior going on, and certainly my experiments will not fit well with taking just the dimension divided by 2. So so I think I should probably not say so much more about the general dimension case, because really it's a hard problem. I think it's an interesting problem. I've showed it to people working in these kinds of math, and you know, it's not my area of expertise, so I'm pretty sure I'm not going to be the one who solves it, but I try to put it out there so people can think about it. But let me end on by going back to just 2D, right? So I'm working in 2 dimensions, and so now I'm just counting buildings that are flat. They sort of live in one layer. So you should think of them, I mean, I can actually do them with my 2x4s, right? I'm just putting everything, either I'm putting them on like this or like this or like that. But then you can sort of look at them from the end and you can see what goes on. So now I will say that a building that I'm counting by Bn in 2 dimensions, it's strict if two bricks are never, they're never put on each other like this. Right, so I'm just saying I only allow this one and that one. So that's a strict building. And then we say that a building is a pyramid if all bricks, they rest on the base brick. And so we can sort of count these strict buildings, and we can count the pyramids. And now you can see I've made my problem a lot easier because I'm just looking at something which is 2-dimensional, and I've even put in extra restrictions. And this will allow me to actually say something with some mathematical depth behind it. So let me just show you exactly, I mean, so this, what I'm trying to do here is I'm counting something with 4 or 3 bricks, depending on your definition, right? So either you say, okay, let's just look at the ones which are 2-dimensional. I'm counting them all, but I only want to see the ones that are strict, right? So you can see all of these buildings are strict. And then if you look at the buildings that you see here, and there's something like 1, 2, 3, 4, 5, 6, 7, I have to move this little window here. So there's 5 here, there's 7, so that's 19. And then that actually comes to 10 in total, because there's 1 which is symmetric. Here it is, right? So you take the 19, you take the 1 out which is symmetric, then there's 18 left, you divide that by 2, so that's how I get to 10. But I can also say I'm counting the strict pyramids. So when I'm counting the strict pyramids, I'm fixing the lower brick, so that now there's a rule that says it can only be 1 brick in the lower level. So something like this one here doesn't count. But then now there's no symmetry to worry about, but I'm only counting the ones that are pyramids. So what do I mean by pyramids? So this means that the definition is that everything rests on the base brick directly or indirectly. So let me show you something which is not a pyramid, like this one here, right? Because there's this brick here is hanging down. That's perfectly fine for Lego. That's actually what this pattern was all about. But that's not a pyramid. So there's 13 of these pyramids. So that means that if you take these 19 configurations, you can throw out the 6, and you get the strict pyramids this way. Okay.
Wait,
so
Søren, and this one is also not a pyramid.
No, that is a pyramid because everything rests on the base brick.
But this one is hanging in the air.
Yes, but it's sort of okay. Yes, so I see what you mean. So this would actually fall down, right? If this had just been things that you placed on top of each other, then gravity would pull it down. But I don't care about gravity. so okay. I would just say that it's sort of sitting on something. So it doesn't matter if I'm sort of thinking of this as being clutched together, so that there's sort of enough gravity that it doesn't fly off into space, but not enough gravity to make it tumble. This is a good sort of point that you're making, because this is really the way. So what's wrong about this one is that it's attached from below. This is what makes it not a pyramid.
Yeah, and this one is not attached from below, so that's not a pyramid.
Exactly.
Okay.
Thanks for pointing this out. This is confusing if you're not. I'm brainwashed with these things. So
yeah.
Okay, so let me tell you something about what we actually know. So so here's 1 brick more. Let's not count. So it turns out that it is very easy to count the number of pyramids. So the number of pyramids is just a basic combinatorial constant. It's the number of ways that you can select n+1 items from 2n+1. And the way I perhaps would like you to think about this is that it's the number of strings of length, say 2n+1, were written with zeros and ones, where exactly n of them are zeros. And so this is a basic combinatorial constant, and this was, I don't know if this goes back further, but I've learned it from a paper of Bousquet, Melou, and Regnitzer, who are sort of famous combinatorialists who do this kind of thing for a living. But if you have this, then you get answers to all of these questions that I asked. First of all, A1700, this is the entry in the online encyclopedia of integer sequences. You can look it up there. But now it's very easy to compute that the nth roots of these numbers and the successive quotients, they will converge to 4. And there's a generating function, which means that if you take these numbers and you put them in front of a coefficients in a power series, like I outlined before, you get a very nice expression. Right? It's 2/1 minus 4x plus the square root of 1 minus 4x. And actually, you can get everything, right? So there's Stirling's formula for n factorial is hiding in here. So you get the constants that I was after. The constant that I called alpha is 2 over square root of pi. This is from Stirling. You get minus a half as the coefficient, and then 4 over there. So the point is that this is a problem which of course is a lot easier than the one that I started looking at, because I've taken down the dimension and I'm saying I'm only counting the pyramids and so on. But still, I get a nice I get an answer, and this answer will tell me that there are these constants that I'm sort of looking for in the general case. So I find this encouraging in the sense that I have to cheat in the way I make the problem easier, but at least I can get data that shows me that in this particular case it works the way that I was hoping for. And I can.
Sorry, Søren, a silly question. What happens for x equal to 1/4?
For x equals to 1/4, so that's outside the radius of convergence of the sequence. So it's that's exactly. So I'm saying that the rate of growth of these numbers is 4. Mm-hmm. So this means that the radius of convergence of the appropriate power series is 1/4. So you're on the boundary of the disk of convergence. It does not converge there. Okay. That's exactly, that always happens for things like this. You can see at this in the function the first time you have a pole or something which is not defined. This is exactly where you get the radius of convergence.
Yep.
So okay. So and you have to be careful with these computations. I always get this sign wrong, but this I'm pretty sure I did it right this time. So I can sort of explain to you where this comes from. So you can sort of take these essentially, I want to look at a string of length 2n plus 2, written with the same number of ones and zeros, but I make the rule that it has to start with a 1. And then you can sort of say, if you have a string like this, then you can translate this into a building by saying whenever you see a 1, you sort of, there's a pointer. Whenever you see a 1, you move this pointer to the left and place a brick. Or maybe you place a brick and then you move the pointer to the, I'll try again. You place a brick and then you move the counter to the right. So the next, I can do this again, right? I place a brick and I put the counter to the right, the pointer to the right. Then whenever I get a 0, I put the pointer to the left. So I move like this, and I place something, I move, and then I'm done. So you can sort of, whenever you have a 0-1 sequence like this, you can build a pyramid using that as a recipe, but you have to be, it has to be positive in an appropriate sense. So actually, so what you need to do, if you have something which is not positive, then you read it from the other end and you swap it and put it back. So I don't really have time to explain that. Maybe you can sort of imagine that there is actually a formula, a recipe for whenever you have a 0-1 sequence, you get a unique pyramid this way. And this is why you know that the number is exactly the same. So I'm a little short on time, so let me just give you a quick idea of what happens when you're doing the strict case, because it turns out that actually, if we look at the strict case, so that's when it's disallowed to put two things directly on top of each other. then you can actually count not just the pyramids, but all of them. So the way you should do this is that you should somehow imagine that whenever you have a brick, so I've shown you only the strict versions. So whenever you have a brick, you should sort of take a 1-by-1 brick and put it on top of that at a 45-degree angle. So you can actually build this in Lego. There's these little 2-by-1s with a little tube. I put this on at a 45-degree angle, and then I have this kind of setting here. And the idea is now you should sort of turn your head 45 degrees and you should squint a little bit. And now you can see Tetris, right? Because what you're encountering here is Tetris, right? It's the so-called tetronymos. These are exactly the configurations that you can get in a plane setting with 1-by-1 cubes that are attached to each other. So what I'm trying to say here is that there's a little bit of symmetry you have to worry about. So you can see, like the purple one, we have 4 times, and the blue one, we have only 1 time. And this has to do with symmetry. The symmetry used for Tetris is not the same as the symmetry used for Lego. So it's a little bit of a problem, but the rate of growth will be the same. So the observation here, which I actually also have from, I'm going to skip this, which I also have from Buchs-Camilou and Regnitzer, is that the rate of growth is the same as the rate of growth of the polyomino. So a polyomino, sometimes also called an animal, is just something that you could do on a square, on a what's it called, a piece of paper with a square grid, and then you just fill in some of them. And then you say, how many ways can I do this with 1? Well, there's only 1. How many ways can I do this with 2? That's a domino. So you can do this in maybe, depending on your notion of sameness, somewhere between 1 and 4. And then you have the trionymos and the tetronymos and the pentonymos and so on. And this is a big business that counting these things, and people have thought about this for decades. And it's actually known, so you can see it's entry number 105 in the online encyclopedia of integer sequences. That makes it a very important entry. So it's one of the first things that we put in. We know that the nth root converges to the same as a quotient, and it's a famous constant, Klarner's constant, called lambda. People have worked really, really hard on estimating it, and it took like 25 years to figure out if it was starting with a 3 or starting with a 4. We only know this for a couple of years. But the point here is that this is a problem which is well studied and is well accepted to be very hard. And in a sense, it's counting Lego buildings, right? So this is what I'm finding encouraging, that, the reason why I'm not able to do the Lego count for the one that I'm really after, I mean, in part, of course, it's because that's not really my area of math. I'm not an expert on this, but also I think it's well established now. This is a hard problem, right? So I don't feel so bad about not being able to solve it. So this is really my main takeaway from this. But actually, we don't know the asymptotics, but everybody agrees that it should be lambda to the n divided by n. So the relevant power is -1. And then you can actually combine, this is what I have over here. These are the strict pyramids. And again, there's a nice formula for that that has been done by a mathematical physicist. But yeah, maybe this is a good place for me to stop.
Okay, thank you very much, Søren. Before we start with questions, let me mention that I had a very similar experience as Søren in Billund. I went to Billund with my kids, and it was also raining, but not continuously. So we were outside as well. And till this day, my son has a backpack which is in the shape of a big Lego brick, and it's a wonderful backpack which he still uses. So yeah, Billund is fun. You should try to go there, not on the rainy day. But now let's go into questions. Any questions from anybody?
Can I have one question?
Of course.
Okay, so because in the title of the lecture was the word entropy, and I started to wonder in which sense entropy in this problem appear, because you know it's a little bit hard to define it sometimes. So I think it's a rather combinatorial kind of way of appearing of entropy.
Yes.
Here. The velocity of the growth of the sequences, something like this. Can you tell me something about it, about the sense of entropy in this problem?
So I think so. It's true. There's this famous quote by von Neumann. So Shannon, the information theorist, had invented this notion, and this is the kind of notion that I have in mind. And he was asking von Neumann what he should call it, and then von Neumann said you should call it entropy because everybody uses this, so nobody will know what you're talking about, and then that will give you an advantage or something like that. So I mean, this is somehow a bit of a joke, but of course so I'm sort of thinking I'm using the word entropy mainly as an information theoretical concept, and this is precisely the kind of entropy that you would say, suppose I have some way of communicating. So for instance, a language, which is maybe something about some 0-1 strings, and you make a rule saying that you're not allowed to put 2 zeros next to each other or something like this. Then you're interested in how many strings are now allowed, and then the next question is how quickly does this sequence of allowable strings grow. So that's what is called Shannon entropy, and this is the kind of entropy I have in mind. But I'm using the word, of course, knowing that for a physicist it means usually something different, right? So it's maybe a dangerous word to use. Another anecdote is that so I did this work with my colleague who's I guess it was around 2005, and we had this paper. We put it on the archive, but it took us a long time to get it published because I think many publishers didn't think it was serious enough. So while we were trying to get it published, somebody else wrote a paper called The Entropy of Lego. And this was an architect who was looking at Lego sets and sort of computing a number which had to do with the number of different parts compared to the number of total bricks. And somehow he was using this to assess the complication of a building. So so I think maybe it's a dangerous word to use, but I think all notions of entropies have the same sort of basic idea that you're trying to give one number that describes the sort of growth of a situation, and so that's the way I'm using it. But of course, I would be perfectly happy to change the definition. For instance, this happens all the time. If you're sort of looking at a growth problem which grows faster than exponentially, like maybe it grows like c to the n squared, for instance, then it wouldn't work to take the logarithm and divide by n and go to the limit.
In this case, is really connected with the velocity of the growth of the.
It is, and this is really all that it sort of captures. And then, of course, in physics, very often an entropy is related to an inverse temperature, that somehow there's a critical behavior around this entropy. And I don't think there's anything like that in my situation.
Okay, so thank you very much.
Thank you. I hope it's not it's a dangerous word to use. I hope I can get away with it. It's a situation, but it's a good point.
Anybody else?
I have a question. So if you choose this Lego bricks at random and properly, carefully rescale your construction, do you expect that some kind of scaling limit appears in this way, whether it falls into some known universality class?
I've never tried this. And I'm also a little bit unsure of how to make sense of it. But so the short answer is I don't know what to expect in a situation. But I'm aware that this is what people do also in mathematical physics. Also, there are many interesting when you do these sort of thought experiments. This has often led to theoretical estimates of what the entropy might be. Right. So there's a very famous. This is Madras, I think, who found some, made some sort of prediction of entropy of some self-avoiding walks or something like this, which turned out after many years of hard work turned out to be provably correct. So I think this is an interesting way of doing it, but I don't think I have the necessary background. So if I can throw the question back to you or somebody else who's an expert on this side, I'd be very interested to know. So
okay, I'm asking this question since those exponents looks a little bit like the critical exponents in statistical mechanics.
It has, yeah, I think, essentially, I've never been able to sort of take the full step into statistical mechanics, but many of the methods that I'm using come from statistical mechanics. And somehow people have invented these things. People who are probably, working at a physics department rather than a mathematics department, even though I'm sure they're very competent mathematicians. But it's somehow, I don't exactly know how to do this. So I'm hoping someday to learn from this, but I think it's a promising way to go. But I have this problem that I'm really a apart from studying math, I studied computer science, and I don't have so much of a physics background. So I need help for this. So
okay, thank you.
I can also say this is a general thing. There's many interesting open questions in Lego math. There's also a coloring problem that I'm working quite a lot on. So if you have sort of a building with 2x4 Lego bricks, how many colors would you need in order to make sure that two adjacent buildings bricks have different color? You can use the 4-color theorem to see that you can get by with 8 because you use 4 colors here, then 4 colors here, and then the same 4 colors. But I've never seen a building needing more than 6. So that's sort of an open question if you can prove that 6 would suffice. So there's lots of I'm sort of collecting these things. But there's many more problems than I can look at myself. So if anybody's interested, I have lots of open questions, and I think this is useful, right? Because it shows to people that even with a little plastic toy, you can generate open mathematical problems. I think this is fascinating.
All right.
Thank you.
Any further questions or comments? Well, I don't see any volunteers. So in this case, let me make...
Sorry, maybe one more. I would have one more question.
Go ahead.
So you mentioned that regarding this construction using 2x1 in dimension d, yes, you obtain some exponent which which were expected, as far as I remember, to be like -1, -3/2, -2, and then you said that somehow something wrong happens. Yes, that
I think it doesn't actually fit even with -2. I don't really have a good explanation for this, but the data I get, it fits well with -1 and -1.5, and then I don't know exactly what the next sort of exponent should be, but I'm pretty sure it's not -2. So it's smaller than that. And I think then depending on what kind of problem you're looking at in physics, there are various predictions of how, there is one very strange constant that I don't remember exactly. It's like a 2-digit number divided by another 2-digit number. So it's a rational number, but it's not a nice rational number. So, I don't know exactly what to expect here, but the data I have does not support that it just grows like the dimension over 2. So that's all I can say.
So, okay, so this would mean that the 4 is the critical dimension. Critical, okay, so somehow this behaves differently.
Yes, that I see.
the
Okay, I see
dimension
what you
4,
mean.
yeah?
Yes, exactly. Yeah, so at the very first dimension, away from the ones that we're comfortable with, I'm predicting that something new should happen. Yes. And I have reasonable size of data for 4. Right, so I mean for 4D, I can count this fairly far. But of course, I mean, what do I mean by fairly far, right? It's an infinite sequence, so I only have, 8 observations or something like that. But that's better than 2. So of course these numbers grow very quickly. So that's a problem.
So I'm asking this since this is very interesting regarding this relation with the statistical physics. Since in statistical physics, dimension 4 is also somehow critical. Quantum field theory.
I see.
Yes, so,
Right. Yes.
So maybe something is happening there.
Right.
Some deeper relation.
Yes. I think that's very likely that somehow that, I mean, the Lego should behave like generic physical systems is what I would somehow expect. But of course, I don't know if that's reasonable to expect because of the rule that I'm only building in the 4th dimension, right? So maybe it's not a full 4D problem.
I see.
That's a little bit unclear. I wish I knew more, but so the colleague that I've worked with, I mean, he's been busy doing other stuff, but he recently retired, and my plan is, so he's an emeritus. So my plan is to keep bugging him a little bit more, looking on this problem, because I think he's actually interested, but he's we all have other things to do. So it's very difficult to get funding for Lego related math research for 2 reasons. I mean, it doesn't sound very serious, and the second reason is people will say, why don't you just get some money from Lego?
Exactly.
And I can tell you, I have tried this many times. So Lego is a very frugal company. They don't spend money on things that don't think are absolutely necessary. So I don't think that's going to happen. But
so they don't want to produce higher dimensional bricks?
Oh, I mean, if they could sell them, I'm sure they would. But so they are. I mean, one thing about them I should say is that they've always been very good at giving me bricks. So whenever I give talks like this, in real life, I have bricks and I can give them to people, and they will just go out and make them for me. So I mean, that's where I get support. But it would be I'm absolutely serious about, I could easily have work to do for a PhD student in this area, but yeah, money is an issue. So
okay, thank you very much.
Thank you.
Sounds very exciting. Anybody else? If not, Søren, could you please go back to screen sharing? I want to make one quick comment, which might be relevant. Perfect, because I exactly want to point at this formula, a Stirling type formula, right? So you remember it from high school, what happens when I put here n factorial and all these numbers. This is a very useful formula in mathematics. And I would like to draw your attention to a similar counting problem. And it's actually the only time that in my paper, I cited a paper from 19th century. It was 1890, whatever. And these are so-called Dedekind numbers. So let me denote them as dn. And the definition is very simple, like with n factorial. It just counts all different free distributive lattices on n generators. And that's an extremely hard combinatorial problem. It's still open till today. I mean, we don't have such an asymptotic formula. And the growth is like double exponential. So what we know for sure is that it's less than 2 to n. Okay, but what we would like to have, and this is where people have some active research in combinatorics, is to have this kind of an asymptotic formula, and it's still completely open. And as far as I know, it's also funny that the biggest number actually computed so far is like D10, not much more. So this, again, it looks like what you are doing, right?
Right.
And this is a very, very natural problem. And you can see where this combinatorics come from, because it's the set of all subsets in the set of all subsets with n elements, right? And a typical example of a three distributive lattice, basically what you have to do, you have to take things that intersect generically. And then you are not allowed to take complements, but you can take all possible intersection and all possible unions, and you look what kind of sets you can get, and that's your free distributive lattice on n elements. Yeah, and it's kind of amazing that the number which can be so naturally defined combinatorially, you don't have any asymptotic formula whatsoever.
I think so this as a general phenomenon in combinatorics is that if you sort of look at a problem, it's very difficult to determine how hard it is, because you have two problems that, you know, one, they look pretty much same level of difficulty, but one has a nice closed expression and one is completely impossible. And so this is, of course, also when I started looking at Lego counts, I was somehow hopeful that, you know, I would be able to solve it, right? Because it, you know, it could be one of these things that had a nice formula. But, you know, now I've been thinking about this for almost 20 years, and I'm pretty sure that there's no sort of no-brainer solution, right? Of course, it might be something very clever, but that's hard to say, right? I mean, you cannot really, when you sort of look at a combinatorial problem, you can't really, from the outset, it could be easy, it could be hard, it could be impossible. So
exactly, there's this huge discrepancy between how difficult it is to formulate the problem and how difficult it is to solve it, right?
Exactly.
The extreme being Fermat's theorem, right? Everybody could understand the problem, but it took 400 years to solve it. And also, you can look for models. If you don't like some abstract lattice theory, you can look for models, and it's very nice that if you look at the canonical affine coverings of, say, complex projective spaces, they give you precisely models for a free distributive lattice. And once we published a paper in which we provided a non-commutative deformation of projective spaces, which preserved this property. Then instead of coverings, we had ideals in a sister algebra, and we could prove that these ideals give a model to a free distributive lattice. So that actually does occur, but we still couldn't count them. We have a model, but we still cannot count how many of them there are. Okay.
I mean, sometimes this works, right? So it's sometimes if you have something which is impossible to count, and then you sort of relabel what you're, and then sometimes and of course if you have C-star algebras, then your probabilities will go up dramatically. So
okay, so
sorry, Piotr,
Søren,
I have one last question, I promise.
Okay, go ahead, fire.
So this original number Bn, counting all this 2x4 Lego configuration, is also listed as a sequence in this online encyclopedia of integer sequences?
Yes.
It is also listed, yes?
Yes, but that's cheating. I put it there. So
okay. Okay, thank you.
I also have a little question. So regarding your discussion which you just had before, is it possible to ask this?
Which, sorry?
Yeah, so my question is maybe a comment. It's very easy in combinatorics. So these problems, they can be easily formulated, but suddenly you're no longer able to calculate that. Take a 5 times 5 matrix, just for example, a 5 times 5 matrix. And now ask the question, how many possibilities do exist to distribute signs of real numbers as entries of this matrix? It's just a 5 times 5 matrix. You see, it's already a large number. And my question is, are you actually working with NP-hard problems?
I think so, but I don't know how to prove it. I must say I haven't thought a whole lot about it, but it seems, I mean, it should be NP-hard.
It appears to me, yes.
Yeah, but of course, the way people always prove the things are NP-hard is that they somehow associated to satisfiability, And I'm somehow thinking, I mean, somebody proved, are you familiar with the game Minesweeper? It's sort of a it's sort of game where you have to be afraid if you press a square, if you get a bomb, then you die. So somebody proved that this was NP hard by sort of embedding a satisfiability problem into this. So I actually looked at this with the idea somehow I could build in Lego some. I mean, this I think is the way that you were trying to prove something like this, but I wasn't able to. I think maybe this is something again. So I was saying that I have a computer science background, but I mean, maybe it's not strong enough to be able to answer this question. But I think it should be, and I mean somehow it should be possible. I mean, you have to rephrase it, of course, because the output of this. I mean, if you're just asking how many ways can you build together n bricks, then if the output is goes to infinity, then of course you will not be able to find. I mean, you will have to somehow say this right? But you could just make it a yes/no question: is the number even or odd or something like that? And that should be hard, I think.
Okay, thank you. Sorry for asking you.
No, it's a good question. It's a good question. I wish I had the answer. So nothing wrong with the question. So.
All right. I think it's time to end this beautiful discussion and this beautiful talk. So Søren, really thank you again. This was very exciting. And now you guys, all of you can see that doing math can and should be fun. I think Søren is a living proof that you can do math and have a lot of fun, and how important it is to be open-minded, because you never know. You never know. This is also a famous lesson from Richard Feynman. I mean, you should be always playful. You never should dismiss something as not serious enough. I'm too serious a mathematician to do Lego. No. Many discoveries come from being playful and childlike. And then all of a sudden it was, my goodness, now I can quantize gravity because I counted all possibilities of building Lego pyramids. I mean, of course, I'm joking right now, but this is how research works quite frequently. Okay, so Søren, thank you again. We end the recording and we resume at 1100 hours.
Thank you.
Cheers. Bye-bye. Thank you, Søren.